and you will tell us something about tropical moduli.
Yes, that's correct. And I will also say something about this transition from logarithmic to tropical. Those are introduced already. So I was planning on starting with the definition of tropical curves that Chris gave last time, but you've just all seen that. So I'm not gonna. If you really want to see it again,
If you're going to use all of the notation from the definition, I would love to see it again.
I will give it again then.
Thank
In that case. So, but I'm just going to use a notation and give a notation. So we have a tropical curve x, GRIL. Well, actually, I can introduce an extra notation now. So G is a set which I'll divide into two parts: vertices and flags, which are also called half edges sometimes. R is a map from G to G, which is only partially defined idempotent. And R stands for root, so it means that on V it's an idempotent, it's the identity even, and on F, so to a half edge or to a flag, it gives its root. And as Rosa said before, we do have kind of missing vertices, so we can have edges going off to infinity in a sense, which means that, so this gives a partially defined part, where, well, so a half edge need not have a root. I is an involution, also going from G to G. And it defines edges by identifying two half edges. And we have L, so it's everything is defined over monoid M, and it's a function to this monoid. And we've got two conditions, so actually we've got some more. So as I said, this is an idempotent, we should say where it's the identity that's exactly on a set of vertices. So if only if x is in V. And we should also say that something is a vertex if and only if it's a fixed point on the involution, because edges go to their opposite half edge and not to themselves. And those are also the only points that have length 0. So every edge must have non-zero length. That is somewhat important. And what we also need, the length of a half edge should be equal to that of its complements. So this is the axiomatization we're going to use. And it's different from what's often used, and there are several reasons for that. I think we'll see most of that in the next session, but the most important reason is that we can define, for example, this tropical curve, where these are not vertices. So there exists a tropical curve, a connected tropical curve without any vertices. And this is going to be an important one later on. Which sounds really, really weird, but I think
Edge without a vertex still has a length.
it does still have the length.
Okay.
Have a length, so we need an L somewhere. Yeah. I think this is necessary for topology later. Not important for this talk. I'm also going to repeat piecewise linear function. So PL functions. And those are denoted lambda. We have two components from So the first component goes to the groupification of the monoid. The second component goes to the integers. And this is because we want all piecewise linear functions to have integer slope. So what do? Of course, the slope on a vertex doesn't really make sense. So we wanted the slope to be 0 there for all vertices. What else do we have? So alpha, so use the slope, alpha is the value, and we can only really give a value to a vertex because on an edge it should change. But what we define is that the value of a half edge is equal to that of its root. And the really important one, I think. I'm first going to write it out. So if we have, so suppose we have an actual edge like this, and we want to, so we have a value here, alpha of x. We want to know the value at the other side. We know that alpha, well, let's say this one is x, and this is actually alpha of r of x, but that's the same as alpha of x. So alpha of x is equal to this. We also know that here we have alpha of I of x. Well, r of I of x, actually. R of I of x. And here we have alpha of I of x, and these are also the same. So basically, if we want to go from one vertex to another, it's the same as going from one half edge to the other half edge. And what we should do is we should add the slope times the length, which is exactly what the slope should be. So this is mu x plus times L of x. And we've defined the length and the slope of vertices so that this also works, I guess.
So what happens, what is the value of an edge with no root? Or is it undefined? Like obviously if its inverse has a root, we're okay, but in the example you gave with just two edges and no roots, then that
could, I mean, it's still defined. I mean, everything here still makes sense, right?
well, R of x doesn't make sense.
True. Okay, so whenever this is defined, I guess.
But my question is, so if R of x is undefined, then alpha of x can be anything? Is that the convention? Or I guess if these are the conditions you've written in for
yes, so in this particular case, yes.
Okay.
But you, like, if, so except for this one example I just gave, every connected graph only has edges which are connected to at least one actual vertex.
Yeah.
So then there's no problem, and in this specific case, I guess you can do
Do whatever you want. Yeah.
Yeah.
Okay, cool.
So it's basically as if the vertex did exist and have a value.
Exactly. Yeah.
So there is a reason that we don't have vertices there, because they're interpreted in a different way, but you could also probably say something about two different colors of vertices or whatever you like. That would work. Although this is somewhat neater anyway. Okay, so we have two things we can do with the tropical curve, and one of them is subdivision. So I'll recall that as well. So suppose we have, I'm just going to draw it. Suppose we have an edge, length L. What we can do is we can subdivide it, so we can find a point somewhere in the middle, make another edge here, one here, and give those two different lengths, such that L1 plus L2 equals L. This is called a basic subdivision. Of course, you can do this for any edge in a graph. You can also also do subdivide several edges. You can subdivide several times, and all of those things will be called a subdivision of a graph. And we're gonna denote that with a parallel. So it's some kind of map. And that's because the map so the correspondence on log curves will also be mapped this direction. So the arrow's going this way. Then we have another thing called edge contraction, which I'll write in more. So as I said, this is all defined over monoid M. And of course we can change monoids. So suppose we have x over m, we have a function, we got a homomorphism from m to n. And the problem is, so in principle this should be very simple. You just apply the function to every value, to every length, and that's fine. The only condition is, the main problem is that length cannot be 0, so we contract every 0 length. Now there's another problem, because we can only contract edges that are actually connecting vertices. So we need that f of, what's the condition exactly? So if f of L equals 0, we need that at least the root of this thing exists. I mean, this was partially defined, but if it exists, then we can map it to 0. So then we define a graph y and give it, so we basically give an equivalence relation by g of y, so that's another, recall in our notation, g is edge, half edges plus vertices. So that's g of x modulo relation, where we basically say that, so Rx is equivalent to x and equivalent to the evolution on x if f of L of x is 0. So we're just getting rid of 0 length edges and contracting. It's really what you think it is. And yeah, so this induces a map of piecewise linear functions as well. So this induces more direction, map from piecewise linear functions on x to those. If you recall from Chris's talk that we also have linear functions here, we do. I'm not going to give them because they're not relevant for this talk, but same thing happens. And as Rosa already gave the definition of a tropical curve over a log scheme, I guess I don't have to give that, so that's nice. But I will use this. So I'll define f and m trop of a log scheme S to be the group points of tropical curves over S. And we're going to see later on what happens if we change S. And if you're familiar with the moduli space of curves, then you know that we should look at I mean, if we want to define this in the tropical sense, we should have some kind of GMN parameter, and we should have stable curves. We don't do that here, so this is the thing that Mulcho and Weiss look at, but we will do that later on for the classification, because in that case, it's better to have it. But this is apparently the only thing we need in our main paper. So, all right. So the tropicalization map is kind of important, so I'll just give it very quickly again. So by this Kato theorem, we have three different kind of stalks, and I'll just write them very explicitly. So we have, I should probably say, this is section 2. So this is log to tropical. And I'm mostly going to repeat what I already said here, but I'm going to explain it a bit more because, well, I think it's going to be quite important later on. So it's best to see it twice, and then you'll hopefully remember a bit more. So remember from this classification theorem we had, if we have a map of, if we have a smooth curve, so it's an x over s, smooth log curve of course, and we have some geometric point in S and some x mapping to S. I'm just going to say how this works in stalks. So we can either have the case where the stalk over S of a monoid is isomorphic to that of X, which was the smooth point. Or in the second case,
M bar on the right.
Ah, yes. In the second case, we had a marked point, so we had some extra m, and I'm just going to write an alpha to have something to refer back to later on. And the third case was a node. Which is, as Lothar said, was a copy of Z, but slightly more explicitly, we have two parameters in one relation. So, and as Lothar has also said, this delta is the important parameter because it's giving us a length on the tropical side. And if you do want to also have unbounded edges, then this alpha is also an important parameter because it's going to be the length of the unbounded edges of the things corresponding to mark points. So let's just do this.
Alpha is not in MS, so what do you mean by length of unbounded? You mean the slope, I guess?
It is in the groupification.
I mean, it looks like you just you take a direct sum, right?
Yes.
So that's a bit strange if alpha is an element of MSS bar.
No, it's not in MSS bar, it's in the groupification of MSS bar because we're taking something. So alpha, what do we have? I think O minus alpha is the ideal marked point or something.
Mm-hmm. Yeah, on M.
X. So, which means that minus alpha should be in there, I think.
I mean, alpha is in the groupification mine is alpha with the groupification of mx x bar, but it just isn't anything to do with. It doesn't lie in the image of MSS bar.
Let's see. I'm pretty sure it should be. I mean, I'm only just copying what they wrote, so we can check this.
Sorry.
Okay, so in this paper, they say this is what's happening.
Okay.
So,
So you say that alpha lives in MSS bar or something, or MSS bar?
no, they're not saying that. But I think no, it's not in here, but it is in here, right? That's basically the point.
Mm-hmm. But if you want it to be the length of an edge, then it should be an MSS bar.
Yeah, groupification again. So
Sure, but it's. But never mind. I mean, we can always talk about it later. But you're not. I mean, you're not treating this case anyway, so let's not worry about it.
well, I was going to give the general definition, but
Okay. But I mean, but alpha just isn't in MSS bar, right? You're taking.
no, it isn't.
full
But
group.
I'm
Or any.
pretty sure its inverse should be, because let's see. Well, I don't know.
Okay.
I
maybe.
haven't thought about it, but I think it should be. But maybe we shouldn't dwell on this.
Sure.
There could be mistakes in there. It's not just a wrong notation. So anyway, define let's say tropicalization. T, it sends a log curve to a tropical curve. So a log curve over S to a tropical curve over S by, well, it is, what is it? It's a dual graph. And of course you should see this locally, so over every point it is a dual graph of the irregularity of that point. Where the length of f equals alpha, if f is unbounded, and we're not sure whether that's well defined now apparently, but okay.
That thing is a bullet point, not a minus sign.
Sorry?
That thing is a bullet point, not a minus sign.
Yes. Oh, maybe I should use bullets.
Yeah.
But bullets could be vertices or a graph or something. I don't know. It can always be ridiculous. Anyway, so it's delta if f and if together on edge. Of the node, well, the node we have there.
But how will unbounded edges? I mean, the definition of the dual graph doesn't generally have unbounded edges in this paper, right?
Well, okay. So what I mean by unbounded edges is that it only has one vertex.
But I mean, how would that arise as tropicalization of, like, the dual graph of a curve won't have an edge with that property?
But we're looking at log curves, so we can have marked points. Marked. So if we have, say,
so but in this paper we don't. Okay.
yes, for example, the dual graph of this would be this. So we have one node which goes to a loop, and we have one marked point which goes to an unbounded edge. That's what I consider the dual graph.
I agree, but okay, strange. Cool. Sorry, I'm sidetracking you. Let me not do that.
Right. So maybe I should say some. No, well, maybe not. I'll say it later on. So this is a definition that we've already seen in Rosa's talk, but maybe it's good to actually check in somewhat more detail what's going on in the case of specialization, because that's basically the only problem we had. So suppose we have a specialization. I'm just writing this out because I had some trouble thinking of it myself at first. It was somewhat less straightforward than I thought at first. So this is in S. Right, so what does it mean that we have a specialization? This gives us a map of stalks in the other direction. So we get a map in this direction. Right? And we know what it did on edges, because so we have this map, so via edge contraction we know what happens on tropical curves. We also know what should happen on log curves. And we want to compare these two. So we had some node, for example, well, let's say we had a node x, y equals 2, some lower coordinates. Then the question is what it means to smooth this node, I think. So we want to say that this is not smooth. Probably T is the wrong thing to do, right? We have T already. Let's use U. U is fine, I think. So we want, so U is not in the stalk of S at T. So it's not invertible over T. But if we want to smooth it, we want to show that it is invertible over over S. And I have not erased that. So if we look at this notation here, we had at a node we had this local equation alpha plus beta equals delta. And more explicitly, if you look at, or if you remember what Rosa said, then this delta actually gets mapped to, so I mean this is just the logarithmic version of this equation. So basically the map epsilon going from m to o, well, let's say mx to ox, should send delta to t to u, right? And so this means that if we have this, then because we have that everything here is valued in the sharpening of the monoid. Remember that m bar equals m modulo O star. So here, over T, it's non-zero, because it's not a unit. And over S, we get that this actually maps to 0. Now the point is that because we're looking over sharp monoids, so alpha plus beta equals delta should equal 0 over S. You're looking very confused, David.
That's okay, I'm often confused. That's how I am. But when you say sharp, I mean they're not. Is it, O star is not the same as M star, right? They're the characteristic ones, but it's not clear that they're sharps. Am I being silly? Probably.
I think
What is the definition of a log structure that M star is O star?
yes, because the structure morphism should be sharp.
Yeah. So, but what, so why is delta 0 over? Oh, S. This is little s.
Yes, over little s.
Okay.
Sort of small s. Because, well, that's basically what we're doing. And because it's sharp, we know that alpha and beta then are also 0. So we do really need this sharpening. And I think that's one of the reasons that we're writing these bars everywhere. So. And this is a subtlety I didn't see at first, so I thought I'd show it to you. I hope now everyone is in their head what all these R, I, and L mean. So if you want to see what happens with piecewise linear maps, which I think we should want to see because it's always important to also look at maps, we need the lemma. And it basically gives a different description of this case 3. This is isomorphic to something else. So we can also see it as pairs of elements in M, where now their difference is a multiple of delta. Chris is looking very confused, so I'm just going to give the actual map. So going from here to here, alpha goes to 0 delta. Beta goes to delta 0. And for anything in M, it just goes to gamma gamma. And it's not, I mean, you can write an explicit inverse to this, and this works. But what's kind of important here is that, so on one side, we have the description of a node locally, and so in the log smooth world. And on the other side, we have exactly the idea of, I think it's still, well, yes, it's still on the board. We have exactly the idea of a piecewise linear function, namely we have two values in M, or in the groupification, doesn't matter, you can groupify all this. And the difference should be an integer multiple of the length. So that's exactly what we have here. We have two values in M, which are the difference, and the values on the different vertices. And their difference is exactly an integer multiple of the length. So what does this say? These are, well, this explains what kind of functions you can have on a node. In the log smooth case, and this explains what you can have on an edge in the tropical sense. So there's a corollary of this. So if S is spectrum of k bar, and x over s is a log curve. Then what we have is that the global functions on the log curve with values in the groupification of monoids, or of the characteristic monoid, are equal to exactly the piecewise linear functions. And the argument is basically what it already said. So this side is a log smooth side, this side is the tropical side. And, well, Molcho and Weiss don't say anything about the linear functions. And I think that's mostly because in the case with no marked points, we're looking at compact curves and linear functions are only constant. So it's not an interesting case anyway. So I haven't really looked into what happens in that case, but you can probably work it out for non-compact things. Alright, so under this tropicalization we can also wonder, so we had some structures on the tropical side, we had these piecewise linear functions, we've seen what happens. We had edge contractions, we've also seen what happens on the log side for that. And now we have subdivisions, so we should also check what happens for those. This is probably the more difficult, the most difficult one of the three. But it does say, I mean, it basically states that if you have a subdivision of a tropicalized log smooth curve, you can subdivide on the log smooth curve itself. So I'll write it down. So we have x over s log smooth. And there's some y going to t over x subdivision. And then there exists a log smooth y over s, which is a logarithmic modification, and I don't think we've seen that, so I'll just say, I'll show you in the proof what it is actually. Although this is the part of my talk I understand least, so if you have comments, please give any. Of x. So we have so we have x, we tropicalize it and we modify it, and it states that we can also do it the other way around. So we can modify it to y, and then t of y should be the tropical y. And the proof has a lot of details about doing everything locally and then checking later on that it actually works if you do everything locally. And I'm just going to assume everything works. I'm also going for the basic subdivision because, well, it's just a composition anyway, at least Ital locally. So we'll just assume that we have, well, I should check my notation. So we have y of x is a basic subdivision, well, let's say a subdivision of an edge. this node, we will write Z. Of course, this node need not be a point because we're looking over a general family. So away from Z, we can take F to be an iso. Basically, what we're doing is we're, in a sense, blowing up Z to smooth it. So, a log modification. Just going to let it be an iso. Let's see. Should there be cable? Ah. So we want to make something with an extra node. And, well, we have a subdivision E, so we can say that, well, if we are local enough, we can, and I have erased that, but I think we all know the local structure of a stalk of a log smooth curve at a node now. So we have this equation alpha plus beta equals delta. And I mean, we can assume that alpha and beta are functions in some u, over some u, and so this is x, and delta is also defined over the image of u. Right, if we do everything locally, this works. And the subdivision means that we have this map. So we had a delta, and we're going to divide it into two parts. So let's say gamma and delta minus gamma. And for this equation to still make sense, we need, well, we don't need just an alpha and a beta, but we need 4 elements. So basically we need alpha and some gamma minus alpha as well. But of course we're working in monoids, so gamma minus alpha might not be well defined. So what we basically do is we look at all the places where this is well defined. So we define, so we have this U, we chose it such that these things are global there. And of course this is it's a log scheme, so it's also a functor. And we let V represent a subfunctor. So the subfunctor of U basically where this gamma minus alpha is actually well defined. And I'm not going to go through all the details, so this does patch. It defines something which is apparently a log smooth curve, so this is the thing we take. If you do want to ask details.
I'm just confused. So what you've written is different from what they've written? They write about alpha and gamma. Alpha and gamma are locally comparable. Is it equivalent? Or?
Yes, that's the same thing.
Okay.
So being comparable means that, so basically gamma, I think it literally means that there is an element such that alpha plus that element equals gamma. Or the other way around, but the other way around is not relevant in this case.
Okay.
So it basically means that this is well defined.
Okay, cool.
And I thought this seems more natural than saying that it's comparable. So I didn't want to introduce that.
Yeah, sure. Sorry, I was just trying to understand the...
So yeah, it is the same thing.
Nice.
Okay, so these are all things we're gonna need later on, I think. So that's why I was asked to introduce them. Now we're going to the interesting thing of my talk, which is about the moduli of tropical curves. Or maybe I should start with just introducing moduli problems, because that's, I mean, we are going to do something with Picard, well, stacks, I guess. And of course that's gonna be some kind of moduli problem, and we want to see what it means. So let's first define the moduli problem, I suppose. So this is 3. Tropical moduli. So the definition they give, or which they say they are going to use, is a tropical moduli problem is a functor or category fibered in groupoids on certain kinds of monoids. And I'm just going to write it FSS. So we've seen FS monoids, and we want their morphisms to be sharp. So that's a second S. And I don't really like the term tropical moduli problem for a functor, but I think in algebraic geometry that's somewhat okay. But as far as I understand, I mean, this is not really a problem to me. To me, the problem is finding whether it's representable or something. But that's probably splitting hairs too much. I mean, I was genuinely a bit worried about this, but okay. So why do we define it just on monoidal spaces? We've been talking about log geometry all the time, and there should be a way of seeing how these compare. And yes, they do compare, of course. Otherwise, we wouldn't have done all the log geometry, I guess. So we can just extend this problem. Of course, if we have a log space, then we have some monoids. So let's just define, say, for, I guess I can write T and P. We can extend it to log schemes. By, what we should do is first define it on the double sections. And I mean, this might not be a nice enough thing, so we sheetify it. And we have already seen one case where we've done this before, because equivalently we can just define it. So equivalently, I guess somewhere here. So f of s we can also see as a collection of local data that is, well, coherent in some way. And But these local data are just elements of the stalks, as maybe should not be too surprising. Well, of course, a function, I mean, this function should be a function valued in sets, of course, because otherwise it doesn't make any sense. And then if we have a geometric specialization, then this should map psi t to psi of s. And if you look at this, of course, everyone realizes that we've already seen such a moduli problem, which is great.